Hello everyone, welcome to the video lecture. In this video lecture, we are going to discuss about designing a 4-bit BCD adder. In this video, we are going to cover the BCD number and binary to BCD conversion. Then we are going to discuss the working principle of this circuit. After that, we are going to discuss the circuit step by step. What is a BCD number? BCD stands for binary coded decimal. If we are having a decimal number, suppose the number is 9, in decimal, its binary equivalent will be 0, 1, 0, 0, 1. So this is the binary equivalent. Now if we have a number, suppose it is 16, in decimal, its binary equivalent will be 1, 0, 0, 0, 0 in binary. Now BCD says that a binary coded decimal number is that number where each of the digit will be represented by a 4-bit binary configuration. So 9 in decimal, its BCD value will be 1001, and in case of 16, its BCD value, each of the digit, that is 1 and 6, will be represented by a 4-bit binary representation. So 1 will be 0001 and 16 will be 0110. So this is the BCD value of the binary of the decimal value 16. So you can see that there is a difference between the binary representation and the BCD representation. But in 9, there is no difference between the binary and the BCD representation. For better understanding the BCD number system, you can follow the video given in the link in the description section. The question arises then to how to convert a binary number into its corresponding BCD equivalent. So for the number, decimal number ranges from 0 to 9, the binary value of this number is equivalent to the BCD value. Now, for number ranges from 10 to 19, the binary value and BCD value differs. So, to convert a number, suppose x, into its BCD value, first we have to check that if x is less than equals to 9. Now, if x is less than equals to 9, so there is no difference between binary and the BCD value. If that is not, means if x is greater than 9 and x is less than 20, so the range is 10 to 19, we need to add 6 to the binary value to get the BCD value. So we can write that BCD equals to binary plus decimal 6, right? Now, for a number ranges between 20 to 29, the conversion will be done using BCD equals to binary plus 12. For 30 to 39, it will be binary plus 18 will give me the BCD. Like this, it will continue. Now, let us take an example. So let us take the previous example. So 16 in decimal, in binary it is 10000. So what is the range? It is between 10 to 19. So we know that we need to add 6 to the decimal value, 6 to the binary value. So 1000 plus 6 is 0110 in binary, and if we perform that addition, we will get 1110. We will get 0110 and 1. So this is 6, and if we pad 3 front zeros, it will not change the number, so I will get 16, right? So this is the BCD value. Let us take another example. Suppose we are having 15 in decimal. So 15 in binary it is 1111. In binary Now it is in between the range 10 to 19, so we need to add 6 to it. So 1, 1, 1, 1 plus 0, 1, 1, 0. I will get 1, 0, 1, 0, and 1. So I can put three front zeros. So I will get 1, and this will give me 5. Now we are going to concentrate mainly in the range between 10 to 19, and there is a reason for this consideration. Now, working principle of this circuit, it takes two BCD number in A and B, and it will perform the addition using IC 7483. To learn more about IC 7483, you can follow the video given in the description. Now, IC 7483 is a 4-bit adder, means it can take two 4-bit input in A and B, and it will perform the addition of A and B, and it will generate result for this addition. So the sum, that is, will be a 4-bit output, and there will be a single bit carry output. Now A and B is a BCD number. By 4-bit representation, we can represent up to 9. For 4-bit input, the and B, 4-bit input A and B both are will be greater than equals to 0 and less than equals to 9. So this is the range. So if we perform addition, A plus B, the maximum value can be 18 and the minimum value can be 0. So the range is from 0 to 18. Now, if the result is greater than 9, then we will add 6 to the result. We know that how to convert a binary, because 7483 perform the binary addition, it will generate a result of binary addition. Now that after getting that result, we need to add 6 to the result of the 7483. Else 0 will, if the number is less than equals to 9, then 0 will be added to the result of 7483. The second addition, that is the addition of 6, will be done using IC 7483, that is a 4-bit adder. So let us go to the circuit diagram and let us take the each and every component. So this is the circuit diagram of this BCD adder. Now, this you can see that there are two 7483. Now, this first 7483 will perform the addition of the two BCD number. Remember, A and B have a restriction that A and B, both of the value cannot be greater than 9, and it will be, the range is from 0 to 9. Now, this 7483, the second 7483 is actually converting the result from binary to BCD. Now, how it is converting that result binary to BCD, that will be discussed. So, let us break that circuit in three parts and let us discuss what is the thing going on here. So, this is the upper part, that is the addition. If Cin is logical 0, so Cin will be 0. So, here we are not considering the Cin. Now, A value is a BCD input, so it values from 0 to 9. 4-bit, by 4-bit we can put up to 0 to 9. B is also from 0 to 9. Now this 7483 will add this value A and B and generate the result S, which is a 4-bit, S3, S2, S1 and S0, and pin number 14 is the Cout. Now the problem is we have to check the summation is the result, that is consisting of Cout and S, greater than 9 or not. Now how to check that? Let us take Z will have the value 1 if the result of the sum is greater than 9, and Z will have the value 0 if the summation is less than equals to 9. So how can I check? How can I configure this one? So as we are adding 0 to 9 in the range between 0 to 9, so maximum result can be 18 and the minimum result can be 0. Now, if Cout is generated, means my summation is in the range 16 to 18. So obviously greater than 9. So Cout will give me from the range 16 to 18. But what about 10 to 16? Now, to check that, we can see that if we go for 8421 code, if a number is greater than in the range between 12 to 15, then S3 and S2 both will be 1. So S3 and S2, if both are 1, then we can say that the result is greater than 10. So S3 and S2. So I can say that if this condition or this condition, then the result is greater than 10. Also, if S3 and S1 in the sum, if both of them are 1, then the result is in the range between 10 to 11. 10 to 11. So obviously it is greater than 9. So S3 if or S3 and S1 both of them are 1, that time we can definitely say that greater than 9. So if this condition, one of the condition is true, that is Cout S3 S2 or S3 S1, one of the condition is true, then we can definitely say that the result is greater than 9. So we need to convert the result into its BCD form. So let us take this value is Z. Now Z will be 1 when the result is greater than 9. Z will be 0 when the result is greater than result is less than equals to 9. Now we are going to prove this expression and this expression is equivalent by using Boolean algebra. So we can write this as Cout double complement or S3 S2 double complement or S3 S1 double complement. Now, so we get Cout or S3 S2 and or S3 S1. So you can see that this one and this one is equivalent. So let us make that Z is this one. Z is this expression. Why we are insisting on this expression is that by this we can implement that logic using only NAND gate. Now here in the previous case we need to use OR gate and AND gate. But here we can implement using only NAND gate. So let us take an example. Here what we are doing, we have a restriction that A and B value cannot be greater than 9 and it will be in the range 0 to 9. So let us take, we are performing 7 plus 2. So A is 7, 0, 1, 1, 1 and B is 0, 1, 0, 0, 1, 0. Result will be 1, 0, 0, 1 with a carry 0. Now, so if we put in Z, so if we calculate Z, so what will be the value of Z? Carry out is 0, S3 and S2 is 1, 0, so it will be 0. S3 and S1 is 1, 0, so it will be 0. So Z is now 0. Clear? So let us put that in the second part of this circuit. So what is the result? The result we are getting is 1, 0, 1. So and Cout is 0. So here we are getting 1. Here we are getting 1, 0. So output will be 1. Here we are getting 1, 0 as an input. So output will be 1. So the NAND gate will have all the three input 1. So it will generate output 0. So Z here it will be, for this example, it will be 0, right? Now this z is also the tens. What is tens? That is in the value between 0 to 18, the 10th position, the position of the 10 is given by the z. So this is my z. Now z, you can see that in this part, the z is going to A2 and A1. Remember, here please understand that here we are using the bar to represent a different number, not the complement. So A3 bar doesn't mean that it is A3 complement, it is just a new representation. So here we are getting Z. Now for this example, Z is 0. So A3 and A0 are grounded, so it is in logic 0. So they are getting 0 and 0. A2 and A1 is getting Z. Here the Z value is 0. So A value is 0, 0, 0, 0. Now B value is 1, 0, 0, 1. It is coming from the summation is directly connected to the B of the second 7483. So from this we are getting that A is 0000, that is 0, and B is 1001, that is 9. So if we perform the addition, the tens is Z, so it is 0, and the result, that is S3 bar, S2 bar, S1 bar, and S0 bar is 1001. Remember, the C in here is at grounded or at logic 0. So this is the final result. I can write 000 and B is 0001, C in is 0. Carry out of this 7483 is not needed. It is the final output is the tens is value of Z, that is equals to Z. So I am getting 0, and the summation I am getting from 7483. So this is my final summation, which is 9. So let us put that into that table. 7 plus 2. So 0, 1, 1, 1, 0, 0, 1, 0. Now the finally we are getting 0, 1, 0, 0, 1. So its decimal interpretation is 9. Now let us take another example. Suppose we are performing 7 plus 5. 7 5 5 is going to give me 12. Now 12 in binary it is 1 1 0 0, but in BCD it is 0 0 0 1 0 0 1 0. So it is in BCD. So let us take how the circuit will act. So I am putting 7 over here. So 0, 1, 1, 1, and I am giving 5. So 0, 1, 0, 1. Now here C out will be 0, and S3 will be 1, S2 will be 1, S1 will be 0, and S0 will be 0. So 7 plus 5, I put it to this one, 0, 1, 1, 1. Carry in is 0, carry out will be 0, and the result will be 1, 1, 0, 0. So it is going to the NAND gate. So I am putting 0 over here, S3 and S2 is 1, 1, and S1 and S0 is 0, 0. So I am putting 1, 1 in this input, and 1 0 in this input. So this NAND gate will generate 1, this NAND gate will generate 0, and this NAND gate will generate 1. So finally the Z will be 1, right? Now if Z is 1, then in the second 7483, the input we are getting here Z is equals to 1 for this example. So input in A is 0, 0, that is always grounded. Now Z is connected here, so 0 1 1 0, that is the decimal 6, and the B input for the 7486 is 1 1 0 0. So the tens is directly connected to Z, so it will be 1, and if I perform this addition A plus B with Cin equals to 0, then we will get 0 1 0 0. So the final output, we can easily put 3 front zeros in the tens. So final output we are getting 1 and 2, which is the decimal 12. So let us put it here. The input to the second IC is 0110. Input from B, that is the summation, is 1100. If we perform the summation, we will get 0100. The carry out will be 1, which is in don't care, because we are getting the tens from the Z. And the sum, that is the ones, place of ones, will give me this value. Now its decimal interpretation is 12. So let us put that into that table. So 7 plus 5 is 0 1 1 1, and 5 is 0 1 0 1. Here tens will be 1 and ones will be 2. So the decimal interpretation is 12. Now let us take another example. Here we are performing, suppose, 9 plus 9. So 9 plus 9, A is 1 0 0 1, B is 1 0 0 1. Then the summation will be, there will be a carry out will be 1, and the result will be 0 0 1. Sum will be 0 0 0 1 with the carry out 1. Let us put it over here. 9 plus 9, it is 1 0 0 1. B is 1 0 0 1. Cin is 0. Sum is 0 1 0 0 with the carry out 1. Now let us put that value into this one. Here carry out is 1 and the result is 1 0 0 1 0. So here's carry out is 1. So here I will get 0. Here I will get 0 0. So I will get 1. Here I will have 0 1. So the NAND getting output will be 1. So this is the input to the 3 input NAND gate, 0 1 1. So Z will be 1. So similarly in our previous, Z is 1. So A is getting 0 1 1 0, and here the B is 0 0 1 0. B is coming directly from the sum. So the tens is like previous, it will be 1 0 0 1 0, that is A, plus B 0 0 1 0. So the summation, final summation is 1 0 0 0. So which is equivalent to decimal 8. Now, so the final output is, the input is 0 1 1 0. Here B input is 0 0 1 0. Summation is 0 0 0 1. Carry is 0, which is in don't care, but the S is coming from Z, which is 1, and the summation is 1, 0, 0, 0. So this is get 9 plus 9, that is 1, 0, 0, 1, 1, 0, 0, 1. Then the result is tens is 1, 0, and the result is 1, 0, 0, 0. That is the decimal interpretation is 18. So by this, we can, by designing this circuit, we can perform the BCD addition. We can perform 4-bit BCD addition. So that's it for today's video. In the next video, we are going to discuss about how to design a 2-bit carry lookup adder.